And welcome to today's lesson. In this tutorial, we will be able to recognize the difference between an equation and an identity, and we'll also begin to verify our trigonometric identities. So we are still in section 6.3 in our textbook. We are on day 2 of that. I'd like to first start off showing you the difference between an expression, an equation, and an identity. So far, we've only been working with expressions. Expressions are just terms that are just sitting there. There's no equal sign. When we introduce an equal sign, we either have an equation or an identity. An equation is conditional, meaning that only certain values of the variable will work. For example, in this equation, sine of x equals 1/2, x could be 30 degrees, that would be true, or it could be pi over 6 if we wanted to talk radians. It could be 150 degrees. It could be 5 pi over 6. There are actually infinite answers that would solve this equation, but not every single answer will solve this equation. X can be 30 degrees, but x cannot be 29 degrees. An equation is limited, it's conditional. An identity will always be true for every value of the variable. 1 minus sine squared of theta will always be equal to cosine squared of theta. It does not matter which angle you're talking about. You could plug in a 30 degrees in both locations, it would be true. You could plug a 29 degrees in both locations, it would be true. You could plug in negative 29 degrees. An identity is true for all values of theta. We are going to be dealing with identities for the majority of this chapter, and we're going to be verifying them. So when we start to verify, we can only work on one side of our identity. Usually we're going to pick the more complicated side because there tends to be more things that we can do to work and solve, verify our identity. So we're going to pick the more complicated side, but understand we're only on a single side of an identity, which means we're only dealing with an expression. So we're back with all the tools that we could deal with in the previous tutorials with expressions. We do not have the luxury of being able to treat it like like an equation. We cannot add something to both sides. We cannot square both sides or anything like that. All we can do are all the tools that we can use on an expression. Okay, so let's look at our first example here. The good news with an identity is we know what it's going to be equal to. For example, we're going to choose to work on this left side because it is the more complicated side. There's more things we can do. But we know when we're going to be finished. We know that this is going to be equal to sine squared. All we have to do is establish that that is true. We just have to show step by step how this will transform into sine squared. So let's start to do that. The first thing I'm noticing is I see a negative angle. That's one of your even odd functions. So I'm going to deal with this first, and I'm going to substitute for that denominator. So the numerator is not going to change right now. Secant squared minus 1. The denominator, I know that secant is an even function. So I know that the secant of negative theta would be equal to the positive secant of positive theta. But actually, it doesn't matter if I know that or not, because I am ultimately squaring this quantity. So whether it was a positive or a negative, I'm squaring, so it will always, of course, stay positive. But it's going to stay positive anyway because secant was even. So that's my first step. I use my even odd. I put a little equal sign that just separates my steps. I'm not going to say equal to sine squared every single step. I just know that it's still equal to. Okay, so now I'm going to split up into two different paths. I'm going to call this path the Pythagorean path. I know we tend to take Pythagorean paths plenty of times. So maybe that's the path that you like to see each time. So I'm going to just rewrite it over here. Secant squared minus 1 divided by secant squared. Okay, I'm saying a Pythagorean path because I know that secant squared has a new name. Secant squared is equal to tangent squared plus 1. And I'm going to replace secant squared with tangent squared plus 1. And then I have that minus 1 over secant squared. This is my Pythagorean path. I replaced secant squared with tangent squared plus 1. Now I see that plus 1 and minus 1 will actually cancel away, and I will have tangent squared divided by secant squared. So it might look a little bit simpler. Let's see what I can do now. I might just change everything to sines and cosines at this point and see what happens. So tangent squared is equal to sine squared divided by cosine squared. And secant squared, if I use the reciprocal identity, is 1 divided by cosine squared. So now I have a fraction of fractions, and when I have a fraction divided by another fraction, if the denominators are the same, I can actually just cancel them away, and it'll just leave the numerators, sine squared divided by 1. So I'm actually finished. I put a nice little check mark when I know that I've verified. So that's my Pythagorean path. Some people might take a different path. I understand that, and I'm going to show it over here. Secant squared theta minus 1 divided by secant squared. Some people might just take the little pretzel path or possibly the butterfly path. I don't know what you'd like to call it. But if you split this fraction up into the two fractions that it's actually coming from and write it as secant squared over secant squared minus 1 over secant squared. Split up the fractions, and now let's see what happens. Secant squared over itself, of course, is 1, and 1 divided by secant squared is your reciprocal. 1 divided by secant is cosine, so 1 divided by secant squared would be cosine squared. So now we're to here, and we all know that 1 minus cosine squared, we're going to be using this so many times, that's one of your Pythagoreans, and that equals sine squared. And we're finished. We know that we're finished because we've achieved the other side of our identity, sine squared. The question is, which path would you see? Would you see the Pythagorean path and go through the Pythagorean identities and then go to sines and cosines and cancel out your fractions? Or would you just do the little pretzel or the little butterfly from the beginning, split up your fractions, reduce, and see what happens? We'll call this the pretzel path. Let's look at our next one. Now I'm using beta. We haven't used beta in a while, so we want to practice that one. We're here to verify this identity. So we're going to pick the more complicated side, which obviously looks like this big old mess here. The first thing I'm going to see on this side is I've got that cofunction identity. I've got cosine of pi over 2 minus beta. I'm going to replace this with the cofunction. So let's see, everything else is going to stay the same. Now, the cosine cofunction, you just simply take off the co and you're left with sine. So it becomes the sine of beta. And I'm just going to use my equal sign. I know that we're eventually going to be equal to that. So now I've got these two fractions. I'm sure they're just dying to be combined together somehow. They don't have the same denominators, unfortunately, so that means I'm going to give the same denominators to them. This one has a 1 minus sign, but it's missing the 1 plus sign. So I'm going to give a 1 plus sign. Probably should put both things in parentheses. Got to do top and bottom. Numerator and denominator. So now it'll have both of those. This one has the 1 plus sign, but obviously it's missing the 1 minus sign. So I'm going to go ahead and multiply in the 1 minus sign factor, top and bottom. And now both of these fractions will have the same denominators. I'm going to leave them in factored form. I had hinted in another tutorial that sometimes I leave them in I always leave them in factored form at first until I realize that the factor will not cancel away. Then I might FOIL or distribute. But I'm going to leave them in factored form for a couple steps to see what happens. Up in the numerator, I've got 1 plus sine times 1. Well, that's just 1 plus sine. Plus, this numerator, I've got 1 times 1 minus sine. So that's 1 minus sine. So that's where I am now. I can see some like terms in the numerator. I see a positive sign of beta and a negative sign of beta, so that goes away. I see a 1 plus 1, and that makes 2. Hey, and that's in my answer. So it looks like we're on the right path here. We've got the 2. Now, obviously, there are no more factors up in the numerator. So these 1 plus sign and this 1 minus sign, neither of them are going to cancel away. So now it makes sense to FOIL them together. So let's FOIL 1 times 1 is 1. The outer terms are negative sign. The inner terms are positive sign. So those will cancel away. And my final terms, my last terms, are negative sign squared. So that's just a simple FOIL problem. 1 minus sine squared, I've seen that plenty of times. 1 minus sine squared, I can use my Pythagorean and say that that's equal to cosine squared. If you get stuck, or if you get lost, or if you're not sure where to go, always look at where we're supposed to be going. We're trying to get this to become 2 secant squared of beta. Right now I've got the 2 where it's supposed to be. Somehow cosine squared is supposed to turn into secant squared. And that makes sense. If you want to see it as a middle step, I'm fine with you going straight to the answer at this point, but to show people, I'm going to put the 2, of course, and then 1 over cosine squared is what remains, because this is like 2 times 1. So 2 times 1 over cosine squared. And there's our 2 times secant squared. Verified. We only took one path on that one. We combined the fractions by giving common denominators and simplified. Let's look at our third one. The more complicated side is the side that I'd like to work on because there's just more things to do. I've got tangent squared plus 1, and that's going to be multiplied by cosine squared minus 1. I can instantly see 2 things. Some people say, let's FOIL, and that's absolutely a fine path. And I'm going to do that as the second example, or as the second path. The path that I see right off the bat is Pythagorean. And I see that because I study my flashcards every day. And if you study your flashcards every day, you might have recognized that tangent squared plus 1 is equal to secant squared. This is secant squared x. And cosine squared minus 1, although that's not actually on one of your flashcards, it's the exact reverse. Since 1, if I reversed it, it would be 1 minus cosine squared. I know that's equal to sine squared, so cosine squared minus 1 would equal negative sine squared. And I know that that must be true because look at the negative sign. I know there's a negative in the answer. Kind of a little way to check yourself. So cosine squared minus 1 is the opposite of what it's supposed to be. So that's the opposite of sine squared. Okay, I'm going to change the secant squared using my reciprocal identity to 1 over cosine squared, because secant and cosine are reciprocals. And I'll just go ahead and put this negative sine squared over 1, just so I can see the numerator and the denominator. Now I'm going to multiply these 2 fractions together. The numerators become 1 times negative sine squared. The denominators become cosine squared times 1. There's my negative sign, and sine squared divided by cosine squared is tangent squared. Verified. So there's our Pythagorean path. Hopefully you see that. If you don't see that, probably the only other thing you can do is the FOIL path. First, outer, inner, last. Let's rewrite the problem over here. And let's see what happens when we FOIL. So first terms give me tangent squared times cosine squared. Outer terms give me negative tangent squared. Inner terms give me positive 1 cosine squared. And last terms give me negative 1. So that's what I get. Those are all 4 of my products. And what's interesting is I already see the answer right here. Negative tangent squared is what everything's supposed to turn into, which means I'm not going to do anything to this. But that means that all of this and all of this must somehow cancel away. And let's see how that happens. Tangent squared I'm going to replace with my quotient identity, and I'm going to say that that's equal to sine squared divided by cosine squared. That times my cosine squared over 1. Now I can multiply these two fractions. I know that there's factors in the top that can cancel with factors in the bottom. I know they're factors because they multiply together. This gives me sine squared. Now over here, I see this cosine squared minus 1 again. Now I know that I see that from the beginning, and if you see that from the beginning, perhaps you're already on this path and you're already finished. But now I can see cosine squared minus 1, and again, that's the reverse of what I wanted, so it's going to be the reverse of what it is on my flashcard. Cosine squared minus 1 is negative sine squared. And now I can see that these two terms, positive sine squared and negative sine squared, will cancel away, leaving negative tangent squared. And there we're verified. So two good paths there. As long as you see something to do, I want you to try something. Look at your flashcards to help you along. Look at the list of strategies that are on your 6.3a notes if you get stuck and you want to do something, if you need to try to do something else. Okay, one more problem to look at. Actually, let's go back because some of you might have been seeing a different way. At this point, when we had the sine squared, you might have seen that we've got sine squared and cosine squared. And sine squared plus cosine squared, remember, makes 1. And then the 1 and the negative 1 would cancel away. There are various ways to show that this term is going to cancel out with these terms. I just chose the one that I happen to see. You might see a different way that cancels things out. And that's what I love about these. There's different paths that we can take. Okay, so we're looking at this one. And I have to pick a more difficult side. And in this case, it's not necessarily easy to see which side is more difficult, except that I see this negative angle right here. I'm going to choose to work on this left side because I see an even odd that I'm going to have to deal with. So I'm going to choose the left side. You can work on the right side and get it to become the left side. That's fine. But I'm going to choose the left side. And I'm going to deal with this one first. I know that cotangent is an odd function. So therefore, the cotangent of negative x equals negative cotangent x. And if we're subtracting a negative cotangent x, that's actually going to change to a positive cotangent x. So that's where I am. Tangent plus cotangent somehow is going to turn into secant times cosecant. Well, there's no way to go straight from tangents and cotangents to secants and cosecants. What we're probably going to have to do is go through sine and cosine land. So I'm going to convert to sines and cosines. I don't have any other strategies really. I don't see any squared, so I can't use Pythagorean. I'm going to use my quotient identities and say that tangent is equal to sine over cosine, and cotangent is equal to cosine over sine. That's where I'm going to go first. Now we're looking at two fractions, and they're just dying to be combined together. Of course, they don't have the same denominators yet. Remember, when you're adding or subtracting, they have to have same denominators in your fractions. So this one has a cosine, but it's missing a sine. So I'm going to go ahead and throw in the sine, top and bottom. So now it has sine and cosine. This one has the sine, but it's missing the cosine, so let's multiply by cosine. As long as you multiply by the top and bottom, the same thing, we're not changing the expression. We're just multiplying by a 1. So now my denominator is going to have a sine, cosine. Yep, it's the same thing. So I can combine these two fractions together and have a sine, cosine in the denominator. The numerator is going to have a sine squared over here, and then a plus, and then a cosine squared over here. So now we've combined the fractions into 1. We have to figure out what to do now. Hopefully people are saying, wait a minute, sine squared plus cosine squared, again, that's your main Pythagorean. Sine squared plus cosine squared will always be equal to 1. So the numerator is 1. So now I've got 1 over sine x cosine x. And I can see the reciprocals now. I can see the 1 over the sine, and if you want to multiply by another 1, that's fine. There's a 1 over cosine as well. So I can see that we have this reciprocal times this reciprocal. So 1 over sine is cosecant, and 1 over cosine is secant. So the question is, are we there yet? The answer is no. We are not there yet. And some of you might be saying, well, wait a minute, I thought we were. No, this says cosecant times secant. But what is it supposed to say? It's supposed to say secant times cosecant. The order is incorrect. But we know that we can flip around the order because the commutative property of multiplication says that we can do that. So I can flip that one there and this one here, and then we have exactly what we need. The reason why I'm showing you this problem is because it needs to be exactly what it's supposed to be. For a formal proof, you cannot stop here because that's technically not the same thing that you need right here. So you have to employ your commutative property and switch around the order. So those were 4 good examples for verifying trig identities. This is 2/3 of the way through our full lesson. I hope that this is making more sense by now. If not, we definitely need to practice more, and please make sure you're watching or you're looking at your flashcards on a daily basis. This really is a whole lot easier if you're able to see the identities as you go. So please make sure you're doing that, and I'll see you in class so we can practice more. Thanks a lot.